1950s with a very hopeful start. And the belief was that if you have an expert system and you feed enough information into it, artificial intelligence would simply jump out of the box. Unfortunately, it was not how it worked out in the end. There was a phase which was called the AI winter, where people were very disappointed about the slow advance in the approach that was taken those days. This AI winter sort of ended in the mid-80s with machine learning became a very hot topic for industrial applications. However, this type of machine learning was still done in a very algorithmic way. So I don't want to go into the details, but the real breakthrough came when deep learning moved into the field of neural network and different computing structures. Now this change in tactics about how to approach AI brought us to today with central processing units or is a tensor processing unit. It's an ideal way to handle AI. Has given us enough computing power to achieve some sort of breakthrough, which is pretty much around the corner. I mean, you see in the media everywhere that AI is going to swallow us in the next year or something like that. I mean, you can see movies from the 1960s predicting AI taking over the world. But now we're at the point where it actually might become true, so we'll see in a couple of days. Of course, AI is sort of divided into two separate sections. So we have the language and image models, which we see online, on the internet and so on. We interacted with ChatGPT, for example. However, very unbeknownst to the majority of people, the embedded in remote AI is the by far more important application of all of this. Essentially, it's linked to the development of robotics. Here you see the very first industrial robot ever, 1961, very interesting shape. The shape changed into what we are known today already pretty soon, and since that, it has been a very rapid development to the point that today we have almost 4 million robots installed in industrial applications all over the planet. So these machines are by far the largest customers for AI and machine learning development. So when we as an educator, of course, are faced with such a fast-moving field, what we want to educate, we are always behind, because to the point that our students actually go into industry, they are a couple of years already behind the curve, and we always have to think ahead how to get this transmitted into the natural intelligence of our students. We start in our education, of course, also with the problem we want to attract students into our university. So we offer these very nice exercises with our school pupils, where the typical exercises are thinking about RoboCup challenge. These are very tiny little robots which have to follow these lines, or they play football, or they find their path through a maze, which gives lots of access to inexpensive components, and yet they can train all the necessary technologies like sensors, electronics, flight mechanics, and so on. But this is not artificial intelligence, as nice as it looks. This is just embedded software running algorithms on tiny MCUs which are embedded in these little vehicles, let's say. Well, if you want to experience real AI, you can log on the internet and open ChatGPT, which is to some point very impressive. However, this is not a real world interaction. As we have seen also from many talks yesterday, it is very important to have some sort of hands-on approach and see artificial intelligence actually interact with the real world around us. Which is, of course, the question, what is a real world interaction with a robot? Unfortunately, most applications look like this. We have a robot in a factory, he's picking up objects from a pallet, dipping it into some oil bath, and that's what he's doing for the coming 5 years, 24/7. This is the typical application for most industrial robots. So we thought that if that's reality, we should replicate that reality. So we organized for us a professional 6 degrees of freedom robot. We only chose the object to adapt with from a very known German manufacturer of kids' toys, these little balls. Our drop-off point will roll the balls always to one end. And well, our palette looks a bit different, but this is just some 3D printed object. And as much as it looks like a toy, this is one of the standard exercises for robots. Depalletize some objects or palletize some objects. All robots are doing this in any factory in massive amounts. To get our robot to interact with the real world, we attach this little camera holder. It's actually quite surprising. The robot didn't have a screw point on this section. I was very surprised. I said, well, actually, I have a little screw here so I can fix it. No, we have to 3D print our holder. The holder will enable the camera to look onto the palette, and that's our entry point for information. This will become important only a bit later. The first exercise, of course, how can students program the robot? Here also we are very lucky that processing power for the control unit has expanded so much that we all have almost touch panel-like interfaces, just like this one. This one is really the software that's running on the handheld programming unit. The software can also run on normal desktop or panel PCs, and it's here in simulation mode. But if it's on a real command unit for such a robot, you can switch to real mode, and then the digital twin and the real robot will move synchronized. Now this is very nice. You can have all these offline exercises where students can program this robot in simulation mode, then you can copy the program and have the robot exercise the program in real world. Our virtual environment here looks very empty, but of course you can populate it with CAD models that you can use. I didn't do it just here for the sake of time. Only the gripper itself I added, but you can have a very realistic environment here in this virtual space. The interface is not unique for this manufacturer. I'm not trying to make an advertisement for this particular company. Here you see the interfaces of many different manufacturers. They all have these days these digital twins and very elaborate graphical user interfaces, which of course makes the usage of these robots extremely easy for everyone, which is of course the selling point. If you have a robot which is so easy to handle that any personnel on a factory floor can program these things, you're saving a lot of money and effort, which is the point about this entire interface. A robot program naturally is just a list of sequential commands. I mean, the robot arm can only be in one position at a time. It's not like a software where you can have multiple processes running in parallel. The robot does one thing after the other, which makes the logic of such a program very much akin to assembler or basic. You have a sequence just moving from top to bottom. If you want to have loops or if then else bifurcations, you have to jump forward or backward in your list. So it's a very one-dimensional thing, which makes this very easy to understand, even for students who have no idea about how programming works in a more complicated environment. I'm pretty sure that this was the inspiration for this list of symbols which represent the different functions. So essentially, each function of the robot is represented by one line with this symbol, and the program will execute one after another. Now, we saw as educators that we can run this interface on a group of computers in a classroom, and everybody would have his nose on the screen, but we wanted to have a more interactive environment where students could discuss more easily with each other. And there I took inspiration from a very fun game which I love to play, which is overriding. In this game, you have to move your robot across this checkerboard floor with lots of rules around it, but the point is that all motion is dictated by the type and number of cards which you get dealt. Then you have to arrange them in some order to move somehow towards the target that you're supposed to move. So it's a sort of same linear approach to how to execute programs. It's quite a fun game, I can really. It's a very geek game, I have to admit. So we thought, okay, let's make some piracy. We simply copied in PowerPoint all the pictures we saw on the professional interface. We printed them out and laminated them. And where is it? Here it is. And we had our little toy cards. Of course, a lot of them. We had a couple of stacks and we arranged these little points. This one, for example, says waypoint. Of course, we had a little presentation beforehand to explain what a waypoint for a robot is. I mean, just coordinates in 3D space. And then we had the students walk around the floor and discuss which commands to arrange in which order to make the robot do the right thing, not crash its tip, not break anything. And once I'm convinced that this thing will not take severe damage, then they are allowed to input this program into the real interface and see what will happen. And what will happen then, I understood that the video doesn't really play, but that's not so bad. Essentially, you then see that the virtual twin here will move, sanitize the objects, and then you can see how the program points move up and down. We're going to play the video. There's another one coming a bit later. This exercise typically takes about 45 minutes, including about 10 minutes presentation, about how the coordinate system of such a robot operates. So that's a very easy exercise, and it's done at this point. The robot is not the point that will execute a real-life shop floor exercise. The more advanced one, we want now to add artificial intelligence into this system. The first task is, of course, to know what you want. In our task, for our deep learning exercise here, please pick only the good colored ones, which are the silver ones, skip the bad ones or other colors, and ignore empty slots. But before you can ignore or pick things, you must first know what he's seeing there. So we use, for this purpose, a commercial deep learning AI software, which is essentially designed for quality control in a factory. So the user can define objects, patterns, whatever he sees or finds in this screen, and then have the AI look for occurrences of such pattern or objects or whatever you are supposed to look, this software is supposed to look for. And the AI will then return whatever it finds as an ASCII list of user-defined names and the positions on the screen. This deep learning in the neural network, I just want to give you a little refresher or appetizer for those who haven't seen this before, is essentially layers of nodes in this forward-facing structure. Our camera gives us 5 million pixels. We feed these 5 million pixels in any order to the input layer, which is then transmitted to the neural net, the execution layer. Surprisingly, actually, that's an interesting fact, these neural nets are not very deep. They have only between 5 and 10 layers. It's the 5 million next to each other, which turns this into a data monster. But you have these days very large graphics cards, you can handle this easily. Once the information flows to the neural net, it will create the ASCII table I was mentioning before, and this is our answer from the artificial intelligence. So to train the nodes in this structure, you have to provide the artificial intelligence enough material to chew on. So its first task is to gather an appropriate collection of images. Now, appropriate is a very expendable word. You have to use the camera in slightly different positions, change the lighting, have a few balls or many balls in different positions. You have to give as much variation to the AI as possible. Now, this as possible, of course, is a stretch. I mean, the students don't have all day to capture all these images. So there must be some compromise somewhere. Step 2, you input all these images into the deep learning user interface, which is here. And of course, that takes a bit of time then, because you have to define the objects, meaning giving them some name, like green ball, red ball, or whatever. You can type whatever you want. Then you have to go through all the images and define, by clicking on it and giving the circle, what object this is supposed to be. So you're teaching the AI what that is supposed to be named. You mark then one half of the images as the training images and the other half as reference images, and you push the button, and let the network train itself. That actually works surprisingly fast. It's about 2 minutes, and the network has found a solution which will then be displayed by this confusion matrix, which means does the system recognize objects where you have defined that they're actually a different one or none, or does the system somehow have funny ideas and see objects where there's actually nothing in the screen? If that is the case, go back to step 1, take more images, train the system again until you have a satisfactory result. Now, here it's perfect. Okay, if you always have to show off. The task is then complete, and you can export the AI into a file onto the hard drive. So the AI part of the task now is complete. But of course, we have some missing pieces here. We have our robot, and we can use the graphical user interface to program the robot. We have our camera giving the image. We have digital interface, but that's not important here. But our AI module here runs on this graphics card. But the question is, how does the image get to the AI? And how does the response of the AI get to the robot? So there's another task hidden here, which then runs on the normal CPU of this unit. You have to arrange the data flow towards the AI and handle the AI results from the AI. this is a very intriguing programming task because it concerns then data handling and transformation of the information into a format that the robot can read and then also take into consideration during the program execution. So it's a more classical IT task. This classical IT task is, in this case, provided by a C# script, which comes on top of the exercise we had before with the graphical user interface, or JavaScript, and training the AI with the graphical user interface situation. Now, here's the video. Now, this exercise, of course, takes quite a bit of time. I mean, the programming of the robot is to be done in less than 1 hour. Training the AI takes about 2 hours. If you want to do everything in a day, well, you're busy all day. Especially writing this C# script is a very elaborate exercise. But there's always this. Oh no, the other one, please. We want to remember this. Yes. Now the big suspense comes in the end. Will the robot do what it's supposed to do? Will it crash, or will it do nothing, or will it do something weird? Yes, please. If all works well, you can see here the image empty. The image is taken, the AI sends the information, and the robot program will continue to execute. It will pick the silver one, place it onto the target. Next one is the blue one. No, he doesn't want that. He will continue with the silver one. So that's the small yeah moment. And students that have the big fun of seeing the robot actually is doing what the artificial intelligence is telling this robot to do. And that's the fun part of the entire day. So this little moment of suspense is what we're all working for. Maybe I simply use this one just in short, otherwise I will jump back to the page for this Okay, so in summary, we have installed an integrated learning environment with industrial equipment, which is the part for the students or school kids, which can say, now we are playing with the real stuff. It's not like a Lego robot we're building. This is a true industrial robot, which is in itself already quite impressive. Although these robots these days cost less than 10,000 euros, but they have become that cheap, so you can buy one and install it in your lab. Our emphasis was purely on the application with a close to real-life application. We're not building here anything. That's what the RoboCup exercise is for. This is just for using the equipment. Now, we have multiple levels of complexity in this exercise. We can, for example, have school kids without any coding experience go through this card and graphical user interface game to get the robot to do something funny and useful. For kids who have some coding experience, we can have them program in JavaScript, which is of course then for the slightly more advanced students, like 15 or 16 years old. For entry-level students, we are preparing a course with fundamental information about how AI actually functions and how they are supposed to understand all the buttons for seconds in the user interface of the deep learning software. I mean, using it is one thing, but configuring it is another. So we have to train our students how to do this properly. In the top level version, for bachelor and master students, they can define and program the interconnection between the AI and the robot. If we have really motivated students, they can do all of it. But this will then take more than a week. And of course, the important part in the end is to have fun with the outcome and all get some fun too and some information with my little presentation. And thank you for your attention.
Your questions?
I'm assuming your students want to challenge the robot with a marble that's not so silver, not quite blue. Do they do that, and how well does the robot picking out something that's kind of on the threshold?
There you have one of the most important questions for industry, because in real industry applications, they're all fearful of that situation. The best way to trick the robot actually is to change the lighting just a little bit. This deep learning software is very sensitive to lighting conditions. We've seen that, for example, the robot will respond differently if the sun shines in from one direction into the room. We have large glass roof. And in the afternoon, when the shadow's on the other side, the AI will already get confused. So that's why industry always prefers having very strong artificial lights spread out everywhere. And that's actually one of the fun parts we do with the students. We let them train the exercise in the morning with that on one side. We don't tell them that they should turn the lights on. And then when they're in the afternoon, the entire thing changes. So it's a very good question, and we use it for tricking our students a little bit to make them learn that lighting is very important.
Another question?
Thank you. I was wondering if there were any students who were proposing to not use AI and just a color picker of some kind. I mean, you're training the AI to recognize colors in empty places, and one could
Do a traditional algorithm.
have a traditional approach that seems kind of more straightforward. Or is it?
For experts, as we all of course are, that it's indeed a probable response. But actually, as the title of the course already says, AI in applications, they're all zooming on AI. No matter what can we do with AI? Oh, we have to program the robot first. Okay, fine. But then we do AI. So they're so keen on running the AI exercise, they're skipping over the entire rest. So they are so keen on jumping to the end, they're forgetting, of course, the part before. So yes, you could do this differently. That's essential. Machine learning was in the 80s and 90s. There the application was indeed more algorithm oriented with color sensors, as we've seen yesterday. I mean, some of you have been in the presentation of our friends from Italy who did this with this Lego installation. Here in this case, they're all jumping straight into the AI. Which is, of course, the entire purpose of this exercise. We want to attract them and say, come to us. We will not eat you. Maybe we'll squeeze your nose, but we have plexiglass sheets around it, so it's not dangerous.
Okay. No more questions. Thank you very much, Christian.
Thank you.